We've been repeatedly told since at least the 1970s that the future fuel for transportation is hydrogen, and that all our exploits in battery electric vehicles are pointless distractions because the hydrogen future will come and take our battery-based lunch. And we've been told that hydrogen's theft of the BEV lunch is just around the corner. The only problem is, it seems like we've been on a Roman road because the hydrogen corner never seems to arrive, and battery technology just keeps improving. But while there's been some argument that hydrogen is an irrelevance, a distraction from the process of decarbonising our energy consumption, an argument that sometimes centres on things like the Tesla Semi, Volvo's VNR and Kenworth's e-Cascadia line, products which look like they might end up taking a big chunk out of hydrogen's road transport raison d'etre. Or arguments that look at the louder and louder pushes to ban new installations of fossil fuel heating and cooking sources from homes. There are still things that it's hard to do with batteries and electricity. And for those things, hydrogen is seen as the way we can have an energy system with more than one primary energy carrier. Hydrogen can be used to provide power sources for those edge case homes for which other sources of energy won't work. And hydrogen will likely find its niche as a way to provide feedstock for industries that have traditionally been reliant on fossil fuels, and as a way to help manage the intermittent nature of some renewable energy sources. Hydrogen is certainly going to be part of our transition to a greener way of life. So it's unsurprising that as the potential from the hydrogen economy has grown and the push to decarbonise has got stronger, that the fossil fuel industry has wanted to get in on some of that action. But the question has increasingly come up, have they just bought some green paint and slapped it on an inherently dirty industry? Recently, we reported on a paper that came out in Energy Science and Engineering called How Green is Blue Hydrogen? And you good folks asked us to have a bit more of a look at it. So here we are. We're going to have a look at how hydrogen is generated now, what the options are going forward, and what Howarth and Jacobson's research says about how clean blue hydrogen really is. And as always, whether it's research that's worth the bother of reading. Perhaps the first place we should start is, what is blue hydrogen? Because for a colourless gas, it sure as hell has a full-on Pride Parade worth of colour. So let's dark side of the moon this thing and see what all these colours are. At the moment, most hydrogen comes from the gasification of coal or lignite, which is, incidentally, basically soft coal. That hydrogen is referred to as brown, not because the hydrogen is a funky colour, but just because that lets you know where it came from. Gasification is a process which breaks down carbon-containing materials into carbon monoxide, hydrogen and carbon dioxide. For coal gasification, this process generally happens above 700 degrees C or 1300 Fahrenheit. This is a pretty old school way of generating gas, going back to the 18th century, where gas for gas lighting often came from gasification of coal. For those of us that remember the old gas plants with their disused gasometers, or even those who remember functional ones, that's from the days when town gas was made by gasifying coal, which was a thing we once did. Humans can be incredibly foolish sometimes. Then there's grey hydrogen. That comes from steam reformation of fossil fuel derived natural gas. Gasification and steam reformation are both non-renewable, carbon-intensive processes that currently produce around 96% of the hydrogen available. So what of that other 4%? Well, there's lots of other options for producing hydrogen. There's everybody's favourite, which everyone likes to harp on about, electrolysis of water. This produces what's called green hydrogen and is the most developed process that's currently likely to result in actual near zero emission hydrogen production. It's renewable energies bay, probably because we know how to do it, and it catches the public's eye. But there are some other more green tinted, rather than actually green, options that have been in the news. Turquoise hydrogen and blue hydrogen. Turquoise hydrogen is a process which breaks down methane into hydrogen and solid carbon. This, like gasification, happens at very high temperatures in a process called pyrolysis. The theory being that you can put the lumps of carbon back underground because burying your problems deep in a hole never leads to problems in the future. And it's super easy to generate the high temperatures needed for pyrolysis. I mean, that's not energy intensive at all. And then there's blue hydrogen, the oil company's favourite, which is like grey hydrogen produced by steam reformation of methane. Well, that doesn't sound very low carbon, I hear your comments saying, and you'd be right. But the cunning bit is that you then use carbon capture and storage. The theory goes that this can halve the carbon output from an otherwise less than clean hydrogen production process. It's a step, say the proponents, and hydrogen's so useful, we should do it, they say. And the first one's free. Oh no, that's something else. So, before we dive into the rabbit hole of whether or not their claims have merit, what other options do we have, and why does electrolysis only make up such a small portion of hydrogen production? Well, let's look at the electrolysis question first. There's a bit of a problem with the catalysts used to split water into hydrogen and oxygen. The most effective electrocatalysts that we have at present are based on precious and somewhat uncommon metals like platinum and ruthenium. And while we've done some very fancy things like, say, coating carbon nanotubes in super thin layers of platinum, which massively reduces the platinum needs, it turns out that making the rather fancy cathode and anode needed to efficiently break down water has proven to be both pricey and difficult. And scaling that up to an industrial process, well, it requires rather a lot of extremely expensive precious metals, which is probably less of a problem for Schmiegel than it is for most companies, who don't seem overly fond of expensive materials being used in their processes. So there's a lot of research into other catalysts that might not work quite as well, but that might be more common and a hell of a lot cheaper. But we ain't there yet. There's also a lot of research into alternative processes, and don't worry, I'm not going to go too far into this because we could spend a year on this and still not have really got beyond the surface. But to give you a little flavour, in tweaks to your basic electrolysis with a catalyst, there's things like solid oxide electrolysis, which uses a ceramic electrolyte. A couple of problems with this. As it stands, it requires very high temperatures, which require a lot of energy to produce, and the process requires 83 times more water than the hydrogen it produces, just to meet the cooling needs. There are also promising avenues for green hydrogen production using excess energy produced from renewable sources, because it's important that energy production more or less matches energy use. Otherwise, to quote Tom Scott, things break. So having industries that can use extra power when it's available and then stop using that power when it's not, well, it's going to be an important step in moving our energy systems forward. There are processes that use sunlight, much less electricity and a catalyst. The challenge with these is that catalyzer materials have pretty demanding requirements, and so far, and this is one of my favourite quotes from a paper for a little while, quote, "Much research has been directed towards the search for such a material. So far, no material performing well in all the fundamental steps has been presented." Or to put it more bluntly, we can't find anything that works. Okay, so electrolysis is difficult and expensive. So how else can you get green hydrogen? Well, there's an enormous variety of ways that we're working on it. There are processes that use anaerobic fermentation or that use bacteria. You can build a biodigester. You can use biomass and water to create artificial photosynthesis in a rather complicated process. You can use enzymes, and that's just the bio-based processes. You can use thermal energy to just straight up rip the water into hydrogen and oxygen. So, given that there's a ton of research into this, then what is the appeal of blue hydrogen? Well, it's kind of available. I mean, throw some carbon capture equipment onto your steam reforming plant, and we already know how to build them, and we have a bunch of them. And Bob's your uncle. You have a somewhat clean hydrogen plant. Or so we've been told. But as is so often the case, the devil's in the detail, and Howarth and Jacobson's research attempts to analyse the actual life cycle emissions from blue hydrogen production, which encompasses a lot of detail. Unsurprisingly, as is often the case in those extremely sketchy articles we've seen before that include every emission they can glom into their EV analysis, then cheerfully disregard anything that they possibly can for gas cars, it looks like the blue hydrogen analyses we've seen up until now have focused on theoretical best and excluded multiple semi-external and external sources of carbon emissions. And that's before we get into the fact that the vast majority of carbon capture technology is still at the demonstration phase rather than the actually scalable and functional phase of existence. So how bad does it look for blue hydrogen, which, as a reminder, is hydrogen produced by heating non-renewable fossil fuel derived natural gas in the presence of steam? Well, to estimate emissions from blue hydrogen production, the authors included emissions from the generation of electricity required for the steam reforming process. As I mentioned earlier, the steam reforming process is energy intensive, requiring around 2¼ kilowatts per metre cubed of hydrogen produced. They did this modelling with the electrical energy required coming from a natural gas plant, as it currently is for most steam reforming plants, because if you're working with natural gas, why not burn it to make electricity? No, don't answer that. Then they also did the same calculations with zero-emission electricity from renewable sources. They also looked at the energy that is put in producing, processing, and transporting natural gas, which, much though many of these companies would like you to believe, does not just magically appear at the steam reforming plants. Then, using estimates of gas vented at production sites and the difference between natural gas produced versus natural gas used in a year, they attempted to estimate what percentage of this fossil fuel resource is lost through leaks and other losses, something that they term fugitive methane. Another energy input they attempted to include in the calculation is that carbon capture isn't free. The methods of capturing carbon that have been used at the 2 blue hydrogen plants currently working in the US, they use electricity. The carbon output from that extra energy requirement also has to be captured, which at present doesn't happen. The study they cite suggests that of the carbon emissions captured from a coal-fired power plant which powered its carbon capture system using natural gas-generated power, well, the equivalent of 40% of the captured carbon dioxide ended up being released by the gas plant. Having put all this together, they calculate it all using a comparison that works out the greenhouse gas output per unit of heat energy contained in green and blue hydrogen, as well as diesel oil, coal and natural gas. And the end result is, well, you can already guess what the end result is. Blue hydrogen isn't green. It's marginally better than grey hydrogen, but at the end of the day, you might as well just burn the natural gas. It's actually more efficient. Even if you source all of the energy from your blue hydrogen for renewable sources, the calculations still don't work. Which should be a surprise to literally no one, because if you've got a thing that requires energy to make it into something else, that energy has to come from somewhere. And unless the energy sources are zero carbon, and your feedstock is zero carbon, then there's going to be some greenhouse gases coming out of that process. As to whether it's a reliable study, well, it looks like the authors have identified their sources for information. They've been really clear about where approximations they've used have come from, and it's very hard to make these kinds of estimations with real accuracy because, curiously, the companies operating these plants never seem very keen to have people actually come and measure things, but within these boundaries it seems to be pretty solid. But as they say, your mileage may vary. But look, this study reinforces that carbon capture at power plants is a waste of our time and energy. We need to go zero emissions, not faff around frobnicating at the edges of our very broken energy systems. But I'm sure you'd worked that out already. That's it for today. If you liked the video, be sure and give it a thumbs up. And don't forget to subscribe to this channel and our other two channels, Transport Evolved Take 2 and Transport Evolved Shorts. We know that while a fair few of you are already subscribed, many more aren't. So go on, hit the bell and help us out. Let us know below what you thought of this video, and remember, play nice. But if you don't like the YouTube's comment section, then why not continue this on our Discord server? It's free and we'll leave the link below. Thanks on behalf to the entire TE crew go out to the folks on my right for being our $15 to $49 a month patrons. Special thanks to our $50 a month patrons, David Jankula, Andrew Martin, Guido Drahoa, Brophy Wolf, Tesla in the Gong, Paul Conway, Sean Ueda, Gordon C, Raging Fellows, Anonymous Freak, Jim Burness, Kyle Hodgson, Anthony Coates, Laura Sanborn, Rory Litwin, and Denny Hyde. And our deepest gratitude to our $100 a month Patreon supporters, John Lyons, Marcel Ward, Reggie Watts, JP Fagerback, Will Graylan, Ellery Hensley, and Ian. If you'd like to join the ranks of our wonderful supporters, you'll find links below to Patreon, Bitcoin and Ko-fi, and of course you can buy your very own TE swag at our Redbubble store. Thanks for joining me, and as always, keep evolving!